So, yeah, this talk is about SQL, and in particular about the SQL ecosystem. And with this talk title, I actually want to address the topic of people that have worries with Flink SQL or with SQL in general. So, is it actually worth it? Like, is it rich enough to power the instant world? Can we power the instant world with 40-year-old legacy? So first, quickly also introducing myself. I have two parts, an open source path and a career path. Career-wise, I was part of all the major startups and companies around Flink. Now the microphone is gone. Everything all right? Yeah, okay. And open source-wise, I'm part of the Flink journey from the very beginning, even before it became part of the Apache Software Foundation. I'm one of the top contributors there, and I'm also actively shaping Flink SQL with other folks in the community. So let's get started. First of all, I have a slide here, what is SQL? But do we really need this slide? I don't think that we need it, right? Like SQL is super popular. It is used in various tools, like it doesn't matter if it's just a search bar in some logging tool or whether it's a big, giant data warehouse. SQL is everywhere. Everybody understands SQL commands. You know how to join data. You know how to filter data using a where clause. SQL is just a super popular thing. So, is SQL the tool that we can also use today? Like, why should we use this 40-year-old legacy in production? So, first of all, let's tear SQL apart and look at the individual pieces, why SQL made it all this way until today and why it is so successful. First of all, SQL is declarative at its core. That means from the very beginning, you were not able to see any files, no threads, no internals, no networking, no resource management, right? Like it's centered around a human language. It's not too mathematical. In theory, you can teach SQL also to your mom or to your dad. There is a ton of code, high level of abstractions behind every SQL keyword. Take, for example, just a select and a select distinct. Just the distinct keyword by itself changes everything under the hood in the optimizer and the planner, but you don't see that, right? Like the engine is abstracting that away from you. And another thing of a declarative language is it performs eager validation. You get immediate feedback if that works or not. So to say, SQL is kind of the earliest YAML that you can think of. But still, there are imperative parts just to get the job done, right? So you have commands like show, describe, drop, or alter that imperatively change the state of a database. And of course, there are also things like SQL scripts that allow you to completely define kind of a procedural way of data transformations. One very big important component in SQL is the optimization. So what does optimization mean? You just declare what you want. It doesn't need to be the most efficient query on this planet. SQL can break apart your object. It's not like an object-oriented programming language like Python or so, where the object stays together. No, the optimizer can break apart the object, can move around pieces, can move around fields, can move around or can remove unnecessary parts of the pipeline. It can also derive common parts, like for example in this case, the optimizer will detect, hey, I'm reading from users 2 times, why not just doing it 1 time, combining the 2 where clauses into one filter condition, and then executing this statement. So for engineers, this whole optimization gives a lot of benefit. For engineers, it means the engine can work on binary data, it can pass pointers, it can do all the crazy optimizations like lazy deserialization and lazy serialization. For theorists, there is also this whole world of relational models, relational algebra, cost-based optimization, all these very mature scientific concepts that exist actually longer than 40 years. And when I did some research on this talk, I actually noticed maybe I should have called this talk 50-year-old legacy, because the first paper around like relational algebra was actually 50 years ago. And I've actually found the first paper, and I also read the abstract of the first paper, and I think it still applies until today, what is written in this abstract here from 1970. It says, future users of large data banks must be protected from having to know how the data is organized in the machine. A prompting service which supplies such information is not a satisfactory solution. Activities of users at terminals and most application programs should remain unaffected when the internal representation of data is changed, and even when some aspects of the external representation are changed. So you can see the problems that they tried to address back then are actually still the same problems that we have today with schema evolution, with query evolution, and all these kinds of changes that make our lives as data engineers and as software engineers difficult. And one of the most important things around SQL is the standardization. So the SQL standard is really a massive legacy over the course of 40 years. So the SQL standard is actually 40 years old. It is the result of really heavy negotiations and endless discussions in committees, in groups, in like also off-topic like drinks or something. It involved various industry leaders, generations of engineers and data experts that try to come up with something where everybody is happy, where you can solve a lot of domain-driven problems and come up with a domain-driven language. And SQL is by far not dead and also not complete. Like if you look at all the SQL standards until today, last year they just released a new version of the SQL standard. So over the course of 40 years, it got continuously new features, new keywords, and new solutions to problems. And this is just the abstract of the SQL standard as of today. So there are certain parts, right, like 16 parts altogether. Some of them got abandoned, that's why it's not in this list. But I think the most important part is actually part 2. And even part 2 consists about of 1,700 pages. So it's a book like this, and I actually had it as a printed version sometime. It is a very useful monitor stand. It's very high, but it's really a massive piece of knowledge and a massive piece of information how you can actually deal with data. So now let's talk a little bit about the state of SQL. How is SQL today? Like what do we want to do, or what can we do with SQL today? So I already talked about the foundation, but what does foundation mean? Like what is this foundation I'm talking about? First of all, SQL has a type system, right? And this type system is famous. First of all, everybody knows its types. It has a well-defined set of types. People know varchar, people know timestamp or array. It has a very strong catalog integration, so you don't need to specify some distant S3 bucket or some Kafka cluster or something like that. No, everything is hidden behind just a single string, right, like T or my table or something like that. And from there, using the type system, you get all the types. You can immediately start exploring and playing around with the data. So catalog integration, a very important foundation for working not only with SQL, but in general, it's a very useful component that you want to have in every API, basically. And then there is schema awareness that comes with catalog integration and a type system. So just take this SQL here, for example. Maybe you don't fully understand what the SQL is doing, but the optimizer and the parser, they still know what's going on here, right? The first pi references the mathematical function. The from pi references a catalog pi, a database pi, and a table pi. And maybe there is a field called pi, and in this field field, you still want to call the field of a field, so you say pi. So like the optimizer is able to understand that and can also validate your SQL query at any point in time. And of course, various built-in functions and operators make SQL nice to use and get the job done if you just want to extract some year from a timestamp, or if you want to just calculate some standard deviation or so. And next to the type system, there is also the ecosystem. And I will not go into the details here because it's just giant, right? Like you have SQL editors, you have JDBC interfaces, you have CDC connectors, you have tools. And yeah, all these tools together make a very good SQL ecosystem and the foundation on which we can build. So the foundation is great, but there is a problem, and I understand these worries. I also get these worries all the time from users working in the Flink SQL space. There is a lot of foundation, but it's not enough for the instant world. Like during the 8 years where I have worked on Flink SQL, I got statements like, yeah, it's nice that SQL is so tightly, like statically typed and so on, and has a schema awareness and everything, but our data has no schema. It comes from a different system. We are not in charge of the schema. We don't know it. We need to process a lot of JSON, so SQL is not a good fit for that. Then other statements are, no, if I would write this in SQL, it would become unreadable. Or another one would be, yeah, that's nice that I can define some analytical stuff in SQL, but there should be a timeout after 5 minutes. Like, how should I express that in a SQL language? Or, yeah, but some events, they come delayed, and I still want to show some intermediate results. Or, yeah, I cannot easily express that with SQL. That's impossible. Or, yeah, and if that and that happens, or this error happens, then I want to send out a different event, and all this stuff, right? Like, there might be also updates coming in. How do we deal with updates? The regular joins, like left join, outer joins, inner joins, they all don't fit to my use case here. I need a special kind of join. Or, I need the entire history in order to calculate this key here. And yeah, as you can see, a lot of problems, and all these problems, they make the adoption of SQL difficult. And this is what Apache Flink tries to solve for a long period of time already. But there is also the standard, and the standard is also evolving. So I talked about like the standard 9075, but there is also a 19075, and this is an extension to the standard. And this extension, together with Apache Flink's capabilities, can also move us forward towards powering the instant world. So what is this additional extension good for? So first of all, this is called the Guidance for the Use of Database Language SQL. It has currently 9 parts. Yeah, some parts are a bit outdated, right, like for processing maybe XML, but there have also been newly additions, and I just want to go into the details of 3 parts of these additions. So part 5 is about pattern recognition, part 6 about support for JSON, part 7 about polymorphic table functions. And what Flink tries to achieve here is we don't want to come up with our own SQL dialect. We don't want to create new keywords for powering real-time use cases. No, what we want to do is we want to perform stream processing. We want to give people the possibility to write event-driven applications, but with existing standards. So our major goal with Flink is we want to streamify mature infrastructure consisting of databases, consisting of various types of connectors. We want to enable people to get real-time insights there, but also being able to consume updates, to also trace updates and changes. So this whole world of CDC, change data capture processing. So how do we do that? So first of all, let's talk about row pattern recognition. This is already in Flink, I think, since 2018. What it allows you is basically, given some input data like this, so in this case we have some stock ticker data with a symbol, some timestamp, price and tax. And how can we now use SQL to answer this question here? Find the longest period of time for which the average price of a ticker did not go below a certain threshold. That is a task. Try to express that in SQL. It might take you some time to get there. But the SQL standard evolved, and what it offers today is the so-called match recognize clause. The match recognize clause allows you to define a pattern. The pattern is defined here in red. The pattern is similar to a regex pattern, and in the define clause below, you define what A and what B in this example means, right? So you can also use some aggregations over the pattern variables, and if they are true, the pattern will take this, or will accumulate the state in the pattern variable. I don't want to go into the details here. There are talks just for this clause and how match recognize works. But yeah, the output data is correct. So in the end, you really get this pattern recognition result with the corresponding average price. So that's great. So let's talk about part 6. Support for JSON has been added to Flink, I think, in 2021. So we have now like dedicated keywords in SQL to work with JSON. So whether to check if the JSON is valid, whether this JSON string is scalar or an object, whether there are certain elements existing in a JSON object. There are built-in aggregate functions that allow you to combine a table or parts of a table into a JSON string. And JSON query for extracting data, or then the dedicated construction functions and keywords to construct JSON using the syntax here. So that's awesome. Can be very useful in today's world. So let's take a look back at what can we achieve with just the 2 parts that I just showed you. At least the first 2 are gone. That's great. But there are still a lot of other issues that are looking for a solution. And there is actually a solution. And this solution is called part 7. Part 7 is polymorphic table functions. It's a weird name, I would say, like what are polymorphic table functions? You have no idea what they are about. But they can actually unlock a completely new category of use cases in SQL. And in this talk, I want to also go a little bit more into the details. What is this about? So, before I will go into the details, I quickly also want to talk a little bit about Flink, because I don't know how familiar are you with Flink. So Flink SQL allows you to define a pipeline, right? It's like similar to materialized views. You define a query up front, and then you submit this query. Flink will execute it for you. And the pipeline can then consume, for example, from Kafka and write to Kafka. But conceptually, you can imagine like working with tables. So if you would materialize the change log into some key value store or into some database, you would actually see the real tables and how the real tables are getting updated. So whenever a row comes in, the rows are ingested into the system. The engine will also produce you some output. And for example, if there is another Alice coming in and we have already emitted a sum, then of course we can also update the output. So we are sending out deletions, we can delete rows in a database and insert a new record for that. So this is basically how Flink SQL works and how you can observe its behavior from the outside. But of course, it also has an inside. And like maybe you have seen the slides before, I usually also include it in every talk that I give about Flink. Flink basically offers you the 4 building blocks that you really need for stream processing. First of all, you need streams, because you want to distribute streams, join streams, you maybe have an enriched stream, a control stream, you want to replay streams. In general, you have some pipelines in the application, right, where data is flowing. And time is a very important component in streaming in general, because you never know when events are coming in. Sometimes you need to synchronize some streams together. Sometimes you want to make progress on one stream and you wait on the other stream, or you wait for a second event, and if it doesn't come in, you want to time out, you want to fast forward time, you want to replay time if there was a bug in your application logic. So various operations are needed around time. Then we have state. State is especially important for joining or for aggregations. You need to store some data somewhere for a short period of time. Could be for a buffer, for a cache. Maybe you want to store your machine learning model in there. And in general, state can grow. It can be very large. But at some point, you also want to expire state. So there need to be some TTL functionality involved as well. And if there is state involved, you also want to perform a snapshot of your entire application. And Flink is very good at that. It can perform snapshots, so-called save points. It can also use snapshots for fault tolerance, so it can restore a pipeline if there was an error and so on. You can use these snapshots for time traveling, for A/B testing and forking. So all of these 4 building blocks in general are just super useful, and every stream processor kind of needs to support them one way or the other. And now let's take a look back, behind or like under the hood of Apache Flink. So let's assume we want to run the example up there, where we just join transaction and payments together. We use an optimization in Flink called interval joins. So based on the where condition, we tell the system, okay, we expect this join to happen between TS and TS plus 10 minutes. So the system can use this information to perform this join very efficiently and also keep the state size low that is required during the processing. So this SQL up there is actually compiled into the following operators. So you have some Kafka readers, they have some state for storing the offsets. You have an interval join operator. Since this is a join operator, you definitely need to store the left and the right side that is coming in for the join result. And since this is an interval join, so a time-based operation, also you need to use Flink's timer services to discard state when it's not needed anymore. So after that, we perform some projection and filtering, and then we write out to a Kafka writer. So what happens in reality is data comes in, data is joined by the interval join, then it is transformed with projection and filtering, and then it is written out as a Kafka message into Kafka. And there are some internal concepts like watermarks. I will not go into the details here, but watermarks allow the system to clean up. It's like a synchronization barrier that flows through the pipeline, a time synchronization barrier. And yeah, whenever watermarks end up at an interval join, the join knows, okay, we are at 11:55, I can at least remove some state that is not required anymore. And then it will flow on and also pass the entire pipeline. So that would be, so what we saw now was some interval joins, some calc. But what people would actually like to have is how can I replace parts like boxes in this graph, right? So I want to have user-defined operators. I want to come up with my own join, and I maybe also with my own logic right after the join. How can I do that? That was a very frequent question that people asked, like, how can I write my own window function? How can I write my custom join? And the answer is also today, you can do that. You can open the optimizer, you can write your own optimizer rule, you can write your own operator, and so on and so on. But first of all, this is a lot of work. And second is, like, how do you actually represent that in SQL? You cannot represent it in SQL anymore. So that would be very custom, very proprietary, like hard to maintain. We cannot recommend that to users. So the system is open source, but no, don't use open source for just hacking around in the optimizer. It will always bite back. So what are our solutions here? And this is where polymorphic table functions come into play. So this polymorphic PTF document is also roughly 200 pages large. Again, very fascinating piece of document, explaining how we can actually achieve user-defined operators in the SQL language. The document has also various examples. For example, a user-defined join, like how you can see it in the upper example. This is copied from the standard. They have an example for reading CSV files. They have an example for executing some R script, so like passing a table into an R script, executing it there, and then emitting it as a new table. So like those two examples by itself, they already show the power of polymorphic table functions, or what they could potentially unlock. So the important properties of these PTFs are they are functions that can take tables. And they can also return tables. That's why they call the table functions. So, and additionally, the standard also introduced the so-called descriptor keyword. The descriptor keyword allows you to pass column lists, so you can also configure the PTF. So the PTF can polymorphically take an arbitrary schema or arbitrary tables, and with the descriptor you can also further configure, for example, the output type. So like the R script here, you pass as parameters what the output type is. And interestingly, not only the syntax is well defined, also the semantics, how the execution should happen, is very well defined. So everything is centered around the concept of a virtual processor. And you see that you have partition by, but you also have co-partition. And all of these keywords, they basically prepare the whole concept for a distributed execution. So like you can fan out the computation to multiple virtual processors, and each processor takes one partition. Either the processor works on row by row, this is called a table with set semantics, or it works on partition. Row by row is a table with row semantics, or if you do a partition by, then the table is based on set semantics. So yeah, again, like this whole PTF thing might be a talk on its own, but it's not there yet, and that is partially true, but also partially not true. So what we have in Flink already is PTF syntax. So PTFs, we don't have PTF support in Flink, but we have the syntax already in Flink. And for example, if you use Windows, we have the new called window TVFs. So we provide built-in functions for tumbling windows, hopping windows, and session windows. And these PTFs already use the new syntax. As you can see, there is a descriptor, and we are passing the table bit into the session PTF. So syntax-wise, we have already PTF support. It's not 100% standard compliant if you compare this example to the example before, but at least there is something for the syntax. But still, we need also like a way for users to really implement their own PTFs. So it's time to actually generalize this and expose basically Flink's full potential also to SQL users. And this is what is currently work in progress. So there is Flip 440. It is in an early draft state, but I hope that we can find consensus in the community to implement this. So personally, I would call it process table function to be closer to data stream API, and also because the polymorphic term also doesn't tell you what this function actually does. But the nice thing is the abbreviation is still the same, it's still PTF. So let's talk about process table function. Again, this is just a draft, so everything can still change, but I just want to show you where the journey goes. If you are familiar with Apache Flink, maybe you have already seen the data stream API. In data stream API, the process function is actually the most important piece, or the most important function that you can implement, because it gives you access to all the building blocks. You can have a keyed process function, so this function is then scoped to a key context. You can define some states, in this case value state, using some value state descriptor. You get your input streams in here. Then you can work on the state. You can also use the timer services here and work with time, set a timer. The timer callback will later fire here. And if you're happy with the result, then you can also use the out.collect and submit events downstream. So this is how the data stream API looks like as of today. But I mean, you see it on the slide. I had to decrease the font size. It's a bit too complicated. There's too much Java knowledge that you need. There are a lot of generics. Generics are here and there, and like, yeah, it's very cumbersome. And the API also grew over time, so it's actually very difficult to declare state and using timer services and so on. And now let's talk about a future design of PTFs. How could that look like? That's part of the flip. It is less code, so I was able to increase the font size and add additional comments. So if I would remove the comments, I think we have like 10 lines or so left. So basically what you can do is you extend from process table function. You can use POJOs to define your state. You define an evaluate method where you give where you get a context, and then in the signature of the evaluate method you define what types of state you want to use and which arguments the function takes. So in this case, it takes a table. The table will be passed row by row, but the whole table is viewed as a set, kind of. And whenever there is some new data coming in, you increase the counter in state, and you can also use timer services. So also exposing timer services like in data stream API to react on time and to in this case count elements, and if there are no more elements coming in, then after a timeout of 1 minute, we also finally emit the result once the timeout has passed, and of course we are also able to clean up all the state and all the timers. So this is roughly how a process table function can look like. Again, exact design needs to be figured out, but this is how it would look like in SQL to call this function. So regular SQL standard syntax for passing a table, partitioning it by user, and then calling this count with timeout function that I have registered before. Two interesting pieces that I would add implicitly. I won't go too much into the details here, but somehow the system needs to know what is time, so which column is the time column for setting a timer and reacting on timers. So like we need to have some implicit arguments for the time attribute. And another one that is interesting for people that know Flink very well and have used Flink in production. I would also suggest that we introduce a UID implicit argument to every PTF, meaning that with this UID we can also restore the PTF when we restart the job. So in Flink, all the state that is saved in a save point is mapped back to the operators based on a UID. And only if there is a UID you can map this state back. So having a UID for every PTF would actually allow us to support query evolution in SQL. But yeah, like this is interesting topic, but we're running out of time. So feel free to read the flip. It's not fully done yet, but yeah, I guess in a couple of weeks it is ready for a final review and also discussion in the community. And yeah, here I also have an example how this query evolution could look like. So you have an initial submission where you passed in this select here, and you gave a UID, and then you want to change the SQL. Maybe the user type is not just 5 anymore, but you want to filter on 5, 7, and 10. And like the UID basically tells the system, okay, map the state back to this PTF, but around the PTF you can optimize whatever you want. You can move around data, you can use the entire foundation of SQL, the type system, the catalog integration, everything. Just please keep this PTF and the state of the PTF where it is. So yeah. Optimizes around the PTF, but the PTF stays constant. That's a very interesting property of this whole approach. So as a conclusion is, right now, I would also agree it's not enough or maybe not good enough for the instant world. We need more features. But if we have the PTF feature, I'm pretty sure that all these questions or like problems will go away. And then we would be ready for the instant world, and I can just recommend reading this flip here. Thank you.